So notes on the Joules law lesson. So page 7 we'll just mark Joules law, okay, straight off the maths tables anyhow. So power proportion to I squared. Now, we're getting that clear in our head anyhow, we have to know that. Okay, page 8 is the experiment, okay, which we've looked at. So remember, heat energy is equal to electrical energy. So remember, we're presuming there is no energy lost to the surroundings, so the heat energy, and that the cup is an insulating cup, so the heat energy gained will be gained by the water, mc delta theta, and the electric energy lost from Joules law, I squared RT. Okay, we've looked at that in our introduction. We rearrange, so delta theta goes on the y-axis, I squared on the x-axis and the x slot, and we're left with RT over MC as the slope. Okay, so we'll write down M is equal to RT over MC. Now this is a really good example. Now, okay, we've two M's. M is slope, so I'll just say mass of water here. Okay, for that. Okay, so now this is a really good example. There can only be two variables in a graph, so we can only have delta theta and I squared. So we have to keep what is the slope constant, because we need the slope to be constant. So all the four variables that are within the code in the slope have to be kept constant, and they're the precautions effectively in the experiment, as we've seen. So let's go through them, and we'll go through from the top left. So the resistance, okay, we try to keep the resistance as constant as possible by starting each part of the experiment at the same temperature. Okay, at the same temperature. We looked at that. So we start at room temperature each time. So there will be a change, there will be an increase in temperature. It won't be quite the same every time, but it'll be pretty close, and the resistance will not change very much. T is the time, so for each current we take the time to be constant. Makes sense. Mass of the water, okay, so we use the same mass of the water each time. We don't need to use the same water each time, but we have to use the same mass of water each time. And C, specific capacity, the specific capacity has to stay the same, so therefore you can't change from water to oil or something else during the experiment. So that's kind of the setup, right? Now, the apparatus is shown, so let's remind ourselves, okay, once again, so it's the same as for Ohm's law. So we have our potentiometer set up to give us our variable power supply. Okay, so now down here we have our variable power supply. So this can move back and forth. So effectively, like this is like a variable battery here. Okay, in this case we're still interested in the current. We have our coil, and we're going back around to complete the circuit. Okay, the coil is in water. Okay, very important, we have an insulated cup. Okay, insulated cup, and we also need to measure temperature, so we have a thermometer. Okay, to measure the temperature. Okay, so what we do, okay, we set the current, let's say to 1 amp. We adjust our voltage so the current is at 1 amp, and we measure the temperature. Okay, we do it for a certain time and measure the change in temperature, and so on and so on and so on. Okay, we've gone through it, so that's fine, and the precaution should be pretty clear. So I don't think we need to go into any more detail on this. As we look at the notes explain themselves. This is NB here. Okay, this point. Okay, so down at the bottom of page 11, we have this. So Joules law, P is proportional to I squared. Now you know if it's proportional, it's equal to a constant. We've done this time and time again. Okay, so constant times I squared. And the constant is R. Okay, so constant for both, and this is important, Joules law and Ohm's law is R, same constant. Effectively, Ohm's law and Joules law are very, very equivalent, but we're not going to go into detail of that. We're going to treat them separately at second level, right? Okay, so P is constant times I squared, so P is R I squared. And then, as we've seen, okay, using Ohm's law, okay, we can change that to P is equal to VI, or P is equal to V squared over R. Both of these are kind of available. It's not quite, but in the tables. This is not, and it's a very handy formula to have, so make sure you know it. Okay, you should really know the three of them. Okay, and remember, for the two of these, okay, and we'll look at this again in a second, this is what we call the dissipation. Okay, so it's the heat losses. If there's heat losses, this is the formula we'll be using. Okay, and if there's energy or heat or energy transfer, we'll say, this is the formula we'll use, and that'll become clear. But just be clear on those, kind of have those learned. These are three formulas you just know, bang, bang, bang. Okay, and remember, we can change any of these to energy by saying, let's take this scenario, P is equal to VI. This is the energy for 1 second. Okay, because remember the power is the energy per second. So if we want to get a formula for energy, we have the energy for 1 second, which is this, multiplied by time. So we have our VIT, so be aware of that. And the same, we just write the three of them down over here, RI squared T and V squared T over R. But good to remember it in that way. Okay, good to remember it in that way. Okay, that's that one. Let's go forward to here. Okay, and the event. Okay, so the effects of electric current were heating effect. So Joules law experiment, electric heaters, kettles. So electric current causes heating, and this is the I squared RT. Okay, chemical. Okay, we'll come back to and magnetic and electromagnet. So I think we're pretty clear on those. These should have been marked. Okay, because we've done them. Advantage using extra high tension. EHT is extra high tension, and basically that's another name for high voltage. Good old-fashioned name, right? Okay, so basically power is lost in the wires due to heating. So power is lost I squared R. So the greater the current, as we've seen with the experiment, the greater the heating effect. We don't want heating in wires for transmitting electricity, because we want to bring all the energy from one place to another. Any heat in the wires is lost, is what we call lost heat, and it's not going where we want it to go. The smaller the current, the less power will be lost. It's important. Okay, clear? Because P is proportional to I squared. Okay. Power transmission is calculated using P is equal to VI. It has to be, because we can't find the resistance. If we want to use R, we'd have to know the resistance of every item in the power station, in the transmission across, and in your house. Impossible. Okay, so it's P is equal to VI, right? And if you look at this, for a certain power, if we want to make the I small, we have to make the B small. So the power transmission is constant. So P is VI, the smaller I, the larger V. Power transmission is constant. What that means is P is constant. That's one that you have to kind of think about. We'll come back to it. If not this year, in September. But try to figure it out. Okay, that's that one.